Now let's zoom in on the 12 soil orders. As I mentioned, these are the broadest classifications. You'll notice that the name for all the orders end with the suffix sol, which is derived from the Latin word for soil. Each order represents a unique set of general characteristics reflecting the dominant soil forming processes and environmental conditions. We'll briefly describe each of them, focusing on their key features. So as mentioned before, there's 12 orders. Now, just to kind of memorize 12 orders and all the details, to me was difficult as a student. So I kind of looked at them into these categories and learned them in smaller chunks. So I have these four categories of vegetation, parent materials, age, and climate. And each one of those have three. Vegetation, these three tend to have certain dominant vegetation types. As you can see, parent materials come from certain types of source materials and form these unique soils. Age, all the way from brand new soil down to very, very old soils. And then, of course, kind of extreme climates. And this is how I kind of would remember them. What we're going to do now is kind of go through the slides and look at all the details for each one of these soils. First up, alpha soils. These are typically found under deciduous forests in temperate moist climates. They often have a light colored A horizon and a B horizon enriched with alluviated clay. Alpha soils are generally quite fertile and make good ag soils. And in the United States, it's about 13% of U.S. soils, and especially in the north central states. Common profile, you got your organic layer, the topsoil A, E for alluviation, that leaching, B with that sub-horizon T, that's standing for accumulation of silicate clays. Not something that I particularly need you to memorize, but just to let you know. On this slide, the picture that you see is the Nebisch series, which is a typical type of alpha soil. Now for our mollisols, the famously rich and dark soils of the grasslands or prairies. They're characterized by a deep, dark A horizon, that topsoil, with high base saturation. We haven't learned what that is. Base is referring to certain types of atoms that are nutrients that will attach to soil particles. Not something you need to really understand yet. That will be explained in soil fertility, but remember that is not has it doesn't have anything to do with pH. These soils typically form under conditions of moderate to low rainfall and are considered the richest ag soils. The rainfall can be one of the limiting factors for growing plants and crops. Mollisols make up about 25% of U.S. soils, dominating, of course, in the plains. And then you have the spodosols. Most often form under coniferous forest conditions in cool, moist regions. They are lightly colored, acidic, and coarse, meaning they have more sand than clay, and they're well drained, often lacking in A horizon, but usually have an E horizon. Their subsoil has distinctive accumulations of iron or aluminum compounds complexed with humus, which stains it darker. That's organic matter. Spodosols are generally, they're poor ag soils. though they can be useful for acid-loving plants like, say, potatoes and blueberries, or for forests. They comprise of only about 5% of U.S. soils, mainly in the Midwest, northern Midwest, and Northeast. Andosols are fascinating because they form in geologically recent volcanic materials. They are typically lightweight, dark, high in organic matter, and easy to till with a high water holding capacity. While they bond phosphorus, an important plant nutrient, tightly, often it makes it less available to plants. But even with that aside, they're still considered a good ag soil. In the U.S., you find them mostly in the Pacific Northwest. You find them in Hawaii and Alaska, but there's not much of it, making up about 2% of our soil, which makes sense because it needs to be located where there's recent volcanic activity. That's where those soils form. Vertisols, these soils form from parent materials that are very, very high in clays. Specifically, clays that have a unique property that they shrink and swell dramatically with changes in moisture. This shrinking and swelling leads to the formation of large cracks, causing a churning effect in the soil, effectively inverting it. Usually the clay percolates through the soil and is deposited lower in the profile. In these soils, the clay is found at the top. And they only form where there are suitable parent materials and climates with a strong wetting and drying cycle, and these soils are unstable for engineering uses for obvious reasons. They are, though, fertile and can be good ag soils, although can be challenging to till properly, especially if it's really wet and it sticks together, or very hard when it's dry. They can compromise like 1% of U.S. soils, most commonly in kind of south central states. In the next slide, I'll show you some cracks here. So typically what we see is what is in the left picture, those huge mud cracks on the surface, but also if you look at a profile, a vertical section of this soil, those cracks extend down through where that clay content is very high. So definitely shrink swell potential here. Histosols are formed from decaying organic matter in wetlands. As you know, the lack of oxygen in these waterlogged environments significantly slows decay, leading to accumulation of organic materials, often exceeding that 20% for organic soils, all the way up to maybe, say, 30%. These are commonly known as peats and mucks, and they have a very low density because they don't have the same amount of heavy minerals in it. Now, while they can be drained for certain crops, they are susceptible to subsidence and even fire when they're dry. Like gelisols, we're going to talk about those. Histosols are crucial large carbon sinks, locks that carbon in the soil. Now, in the United States, there's only about 1% of U.S. soils, and they're usually found in like northern Midwest, and there's some places along the Atlantic and Gulf Coast you can find these. And something interesting, drained wetlands and peatlands are more gelisols because that's where it's very cold, contribute significantly to global carbon dioxide emissions. So as that organic matter begins to decay while it's dry, it releases carbon dioxide. Inversely, if you re-wet these wetlands and saturate the conditions, you can reduce that emissions. Now we're talking about some age ones. The entosols are essentially young soils. They lack well-developed horizons. They barely have horizons at all. This can be because, they're very, very young. Or it could be because conditions inhibit soil development, like, say, extreme climates, or you have a parent material that's very resistant to weathering, or even due to erosion, and stuff gets washed away too quick, or deposition. They are the least developed of all the soil orders, extremely variable, found throughout the country, making up about 8% of U.S. soils. Very simple profile. It's got an A and it's got a C. So that's nice. In the image you see, I think that's the Zimmerman soil, just kind of showing that you have this very weak horizon development there. Inceptisols are another young soil, but they are slightly more developed than entosols. You start to see weakly developed horizons with a typical profile being A, topsoil, B, W is kind of like weakly defined, or it doesn't have much soil, clay accumulation, and of course your C. They're very variable in nature, just kind of like the endosols, scattered across the U.S., but it does make up about 16% of our soils. The altisols are highly weathered soils, old soils, found in warm, humid climates. They're not as extremely weathered as the next one we're going to talk about, the oxisols. They exhibit low base saturation. You don't really know what that means yet, but again, base is going to be certain elements that are attaching the soil. Particles means that there isn't much of those attached. And their topsoil can be quite acidic, often inhibiting crop growth. The subsoil typically has alluviated clay and these are often reddish. While these soils aren't naturally fertile, altisols can be used for ag with proper fertilization and liming. They make up about 13% of U.S. soils, and you think about it, red soils, where do you see that? Southeast U.S. Now, aerosols, on the other hand, they're the soils of, where do you think? Arid climates. Think cool to hot deserts and also shrublands. Their development is limited by, of course, lack of water, and they often have alkaline base and salted horizons. Why? Well, that we don't get a lot of water to leach that stuff out of the soil. It ends up getting deposited. Unless it's irrigated, they aren't very productive for ag, but many in the western U.S. are irrigated. They make up about 12% of U.S. soils, predominantly out west. And, you know, you've probably been learning a little bit by now some of the downfalls of irrigation. U.S. soils are susceptible to it as well. Oxisols are at the other end of the spectrum in terms of weathering. They are highly weathered soils of the tropics, okay, opposite of the aerosols. Their A horizon is very low in organic matter. It is largely composed of iron oxide clays, giving them a characteristic red and yellowish color. These soils are very challenging to manage for agriculture, because you have so much leaching, all the nutrients get rinsed out, probably tend to be slightly acidic. And in the US, oxasols are actually kind of rare, found only in Puerto Rico and Hawaii, so accounting less than 1%. Now, the tropics, we go to Costa Rica, you'll see these types of soils. And our last order, the gelisols, they are the very cold soils, characteristics of the tundra, cold deserts, high mountain peaks. A defining feature is permafrost in the subsoil. Their surface often consists of peat because the cold, wet conditions inhibits organic matter decay. They show signs of disturbance from freezing or like freeze-thaw cycles, and they're considered very fragile, healing slowly from human impact. Also, I mentioned this earlier, gelisols are a very large carbon sink. In the US, you primarily find these in Alaska. In Canada, these are the soils that form massive peatlands, and that is where our peat moss is harvested for, using it as a soil amendment.